So one of the last things we're going to look at in regards to least squares regression has to do with the value of what's called r squared. So some different things with r squared. R squared is referred to as what's called the coefficient of determination, and r squared measures the fraction of the variation in the values of y that is accounted for by the least squares regression line of y on x. So just remember that whenever you're gathering data, data has variability, and the less variability that a data set has, the more accurate your predictions tend to be because of that. So when we're talking about the standard deviation of the residuals, that gives us a numerical estimate of the average size of the prediction errors. So the other thing that we're going to use to sort of go over some different things with prediction errors is this value of r squared. And we've talked about how to find that value in your calculator. So there is a formula for how to compute r squared, and that's this value here. Now we're going to use our calculator to compute the value of r squared, but just want to kind of go over with you just some different things of where r squared comes from, and then we're going to get into some different things with your calculator. So here's the graph for body weight versus pack weight, and if we needed to predict a pack weight for a new hiker, but we didn't know what each hiker's weight was, we could use what the average backpack weight was as our prediction, and that's what this horizontal line here represents. So in terms of just some different things how this involves r squared, if we use the mean backpack weight as our prediction and the sum of the squared residuals, this comes out to be 83.87. So that is, if I take the residual value of each one of these points and I square those distances, that's what this value ends up being here. And then if you take the least squares regression line that we use to make predictions, and the sum of the squared residuals is 30.90, what we would get from this is an r squared value. Whoops, I want to do that. Sort of erase this here. So we would get an r squared value of 0.632. So therefore, what that means, and this I think is more of what we're going to look at as far as r squared goes, is because this r squared value is 0.632, what that means is 36.8% of the variation in pack weight is unaccounted for by the least squares regression line, which means that with this here, that 63.2% of the variation in backpack weight is accounted for by the linear model relating pack weight to body weight. So the higher the r squared value, the more variation is accounted for by the least squares regression line, and the higher the r squared value, the better your regression line is going to be in terms of using it to make predictions about your data. So in terms of interpreting the r squared value, because most of what we're going to do with computing r squared is going to be in your calculator. So if you're asked to interpret the r squared value, this is the sentence structure that you want to use when you do that. And basically what you want to say here is the least squares regression line accounts for blank percent, and that's the r squared value, of the variation in whatever the response variable is. And we'll talk about some different examples of that in a moment here. So both the S value, which is the standard deviation of the residuals, and the r squared value are calculated using the sum of the squared residuals, and both measure how well the line fits the data. However, S, and this is just some different things involving units, S is expressed in the units of the y variable, whereas r squared is a percent, and that's going to be between 0 and 100. So just some different things in terms of how you express your answers for both of those things there. So checkpoint questions here. Why don't you take a moment and see what you could do with these two questions on your own. So with number one, you have for the least squares regression of fat gain or non-exercise activity, the r squared value is 606, and it says, which of the following gives it a correct interpretation of this value in context? So for this particular question here, the answer to this one was C, because what we would say about this, if we were interpreting this R squared value, we would say that 60.6% of the variation in fat gain is accounted for by the least squares regression line. And then for number 2, it says a recent study discovered that the correlation between the age at which an infant first speaks and the child's score on an IQ test given upon entering elementary school is negative 0.68. That's the correlation value. That's the value of R. A scatter plot of the data shows a linear form. Which of the following statements about this finding is correct? And the answer to this was D. And we would say that there is a moderately strong negative linear relationship between age at first spoken word and later IQ test score. So remember that correlation, which is what this value was here, this is the R value, not the R squared value. So just kind of keep that in mind when you're talking about the difference between the value of R and the value of R squared. So a couple different things about R and R squared. So one of which is this: if given the value of R squared, and you're asked to find what the correlation value is. So remember, the correlation value, the variable for that is R, okay? Consider the direction of the association. So remember that correlation can be both positive or negative. And that is, you have R is equal to plus or minus the square root of R squared, where the plus or minus is determined by the direction of the association. Just remember, positive association is as one variable increases, so does the other. A negative association is as one variable increases, the value of the other decreases. So that's important when you're converting from R squared to a value of R, is to know what the direction of the association is, positive or negative. So some different things with just interpreting some of the values if we already know what kind of some of these values are. So this is an example of a summary statistic, and it gives you here just some different things involving a data set, and instead of giving you what the data values are, it gives you a summary. So in this particular data set, you have the slope value here, which is what this is here, and then you have the y-intercept for the least squares regression line, and that's this value here. Then you have the standard deviation of the residuals here, and you have the R squared value here. So in terms of just doing some different things with some values like that, you have some different things to keep in mind with correlation and regression. So one is, and this is a big one, and we've talked about this before, is the distinction between the explanatory variable and response variable is important when you're talking about regression. So just remember that your explanatory variable is what you're trying to use to explain the effect that it has on the response variable. So just keep in mind that with explanatory variable, when we're talking about scatter plots, the explanatory variable is always graphed on the x-axis, the response variable is always graphed on the y-axis. So that's one thing to sort of keep in mind with this. The other is that correlation and regression lines describe only linear relationships. So just keep in mind that it's very important that you plot your data first before you start to get into doing anything with your DOFs, your directions, your outliers, your form, or your strength. The other thing here, correlation and least squares regression are not resistant, meaning they are strongly influenced by points that do not fit the overall pattern. So here is just a graph of some data that we're going to look at in a moment, and it has the age at which a child speaks his first word and what their score is on a later aptitude test. So this is the scatter plot, and then this is the residual plot that goes with this. So I think you can see here that there are 2 points in the graph, here and here, that don't really seem to fit the overall pattern. So those points are going to strongly affect the equation of the least squares regression line. They're also going to strongly affect the correlation. So let me sort of get rid of these lines here. So what you have here is just some different regression lines that are drawn, and correlation values that are computed by taking away those 2 points. So you have over here, here's the correlation value and the least squares regression line with all 19 children included in the scatter plot. If we take out child 19, if we take that point out of the data set, notice the correlation value gets stronger. And if we take out child 18, notice that the correlation value gets weaker. And we'll talk about sort of some of the reasons as to why that occurs. So some different things involving those 2 points. And it has to do with points that are outliers versus points that are what are known as influential. So what we would say back in this graph here is we would say that the point here for child 19, okay, and this point here for child 18. Child 19, because taking this value out of the mix, even though it doesn't fit the overall pattern, we would say that this point is an outlier because taking that point out increased the value of the correlation. But child 18, we would say, is an influential point because taking that point out clearly decreased the value of the correlation. So just some different things as far as the difference between those 2 types of points. So an outlier is an observation that lies outside the overall pattern. Points that are outliers in the y direction, but not in the x direction of a scatter plot, have large residuals. Other outliers may not have large residuals. So when we're talking about outliers as far as scatter plots go, we're looking for points that are outliers in the y direction, points that have large residual values. Whereas an influential point, if removing that point would drastically change the result of the calculation, meaning drastically change the correlation value, it would drastically change the result of the least squares regression equation. Those points that are outliers in the x direction of a scatter plot are often called influential on the least squares regression line. Okay, and those points have the opposite effect of an outlier, where removing an outlier actually increases the value of the correlation. Removing an influential point will actually decrease the value of the correlation. So with looking at these 2 points on the graph here, notice that with let me come back to the scatter plots here. So here's the residual plot. So notice that this point here has a large residual value because it has such a far distance from that regression line here, where child 18, notice that it has a sort of a large distance in the x direction, but not really a large distance in the y direction. So we would refer to a point like that as being influential. So in terms of just some other sort of things here, correlation does not imply cause. So just remember that when you have association, if 2 variables seem to be associated, it doesn't mean that one variable has to have some kind of influence on another. What we would prefer to say is we have data that seems to suggest that sort of notion. So example I gave you here, sort of a kind of a silly sort of thing, but it says a serious study once found that people with 2 cars live longer than people who only own 1 car. Owning 3 cars is even better, and so on. And it says there is a substantial positive correlation between the number of cars X and the length of life Y. So I think there's a lot of different reasons that you can give that somebody who owns more than 1 car or multiple cars would maybe have, or would tend to live longer. And it may not be directly related to just the number of cars that they own. So, if you had, for instance, somebody that owned multiple cars, maybe from a financial standpoint, maybe they're pretty well to do, and, because of that, they can afford maybe better medical care than somebody that has less cars. So, one of the things you want to make sure that you don't fall victim to when you're talking about data is you don't want to, just because you have data that suggests something, that doesn't make it true. It just means that you have data that suggests that there could be a relationship between two different variables. So the last example I wanted to show you here, and it has to do with some different things involving the four-step process. So the question says, does the age at which a child begins to talk predict a later score on a test of mental ability? A study of the development of young children recorded the age in months at which each of 21 children spoke their first word and their Gesell adaptive score, the result of an aptitude test taken much later. And here is the data in the table. So just notice the data that they collected. They have the children in each one of these that are numbered 1 through 21. Okay, and just keep in mind with something like that when you're collecting data for something like this, it's always a good idea to leave the subjects that are in the data. Make sure that they're anonymous. So the reason that we number them is so that we don't know who the children are that are in the study. So what they give you first is the age at which the child speaks their first word, and then what their score was on this adaptive score test that's done much later. So if we're talking about the four-step process here, the first thing I want to do is the state part of this. And the state part of this says, can we use a child's age at first word to predict his or her Gesell adaptive test score? And how accurate will our predictions be? So that's the state part. Remember, in the state part, you want to state what the question is asking you to do. So then we have the plan. So a couple different things with the plan. Well, first we want to start by making a scatter plot, okay, with age as the explanatory variable and their score on the test as the response variable. And if the graph shows a linear form, because remember, we always want to check form first, we'll try to fit it with a least squares regression line and then make a residual plot, and the residuals and the S value will tell how well the line fits the data and how large the prediction error will be because of that. So the do part of this, I'm going to make a scatter plot. So you get something that kind of looks something similar to this here. And because of the way the scatter plot is shaped, the scatter plot shows a negative association. And that is the children will begin to speak later, will tend to have lower scores on this test. The overall pattern for this is moderately linear because the R value here is negative 0.64. There's two outliers in the scatter plot, child 18 and child 19. We would say that child 18, because their residual value is very small, we would say that this point is influential. Child 19, because their residual value is much larger, we would say that this is an outlier. So as far as a conclusion goes for this, or just kind of going through what the least squares regression line for this is. So you have y equals 109.8738 minus 1.1270x, and we're just basically getting that right from your linear regression screen on your calculator. The slope suggests that for every month older a child is when she speaks, their predicted score will decrease by 1.127. So just notice it's decreasing because the value of the slope is negative in this case. So since a child isn't going to speak their first word at age 0 months, the y-intercept in this particular instance doesn't really have any statistical significance with this type of example here. So here's the residual plot, and you have, once again, just the least squares regression line as a horizontal line in this case. So when you have, for something like this here, the standard error of the residuals, that's the standard deviation of the residual values, that's 11.023, and the R squared value is 0.41. So what we would say here is that in terms of interpreting that value, 41% of the variation in the scores is accounted for by the least squares regression line. So that leaves 59% of the variation in Gesell scores unaccounted for in the linear relationship for these data. So since this value is on the small side, okay, what that means is our regression line here, and you can see there's a lot of variation in your points with this in terms of how close the points are to the least squares regression line. Not sure how good this line is going to be in terms of using it to make predictions about some other data values that aren't in our data set. So the conclusion here is we can use the equation score equals 109.8738 minus 1.27x to predict a child's score on the test from the age at which the child first speaks. Our predictions may not be very accurate, though. On average, we will be off by about 11 points on the score. And also, most of the variation is not accounted for. 59% was not accounted for by this linear model. So we should hesitate to use this model to make predictions, especially until we better understand the effect of the two outliers, child 18 and child 19, on the regression results. So that's just a quick example of a scatter plot problem involving the four-step process and some of the things that you want to speak to in that four-step process. So a couple just sort of points here at the end. One is there's no rule for determining outliers or influential points in a scatter plot. You know, the thing that you want to do for something like that is take away the points and recalculate the correlation value just to see what effect it has on that. Always know what would happen to the correlation, the slope, the y-intercept, the standard deviation of the residuals, and the r-squared value when points are added or removed from the scatter plot. And you can do that in a real quick and easy way in your calculator. And a good way to investigate a data value's influence on the data set would be to temporarily, just notice I bolded, temporarily remove it and see its effect. So that's always a good way to take, as far as influence go, some of these things that are sort of spoken to in that second line there. So here's just some summary type things that go into lines of regression, slope, y-intercept, some different things with extrapolation, as well as some different things with the least squares regression line, some different things involving residuals and the standard deviation of the residuals, with some of the things that we've looked at in this lesson here.